In this lesson, we're going to look at the probabilities we get from flipping coins, one of the standard examples that's used to motivate the concept of probability. So we're going to take a look at flipping a coin one time. And if you do that, there are two possible outcomes. And those two possible outcomes give us a sample space. We either have a heads or we have a tails. And we define probability in this context as the number of winners divided by the total number of possible outcomes. So if we flip a coin one time, we ask for the probability of heads, one winner, one heads, out of two possible outcomes. Similarly, if we ask for the probability of tails, one winner out of two possible outcomes. So flipping a coin once, we expect probability of heads to equal a half. We expect probability of tails to equal a half. Now if we flip a coin twice, we have different sorts of options. But our first goal is going to be to identify the sample space. Now you recognize if you flip a coin twice, you could have 0 heads, 1 heads, or 2 heads, but they're not all equally likely. When we define the sample space, we want all of the outcomes to be equally likely, so we're going to break it up into two parts. If we flip a coin one time, our possibilities are either heads or tails. Now for the second flip, how is that going to work? Well, if we have heads on the first flip, the second one could either be a heads or a tails. If we have a tails on the first flip, the second one could either be a heads or a tails. So you'll notice knowing the first one is a heads, the second one is either heads or tails. Knowing the first one is a tails, the second one is either heads or tails. And that gives us our sample space for flipping two coins. HH, HT, TH, TT. Indeed is our sample space. So if we flip a coin twice, the probability of getting two heads, this is our only case, one winner out of 4 possibilities, 1/4. If a coin is flipped twice, the probability of getting one head and one tail, well, here's one head and one tail, and here is one head and one tail. So that's 2 possibilities out of 4, which reduces to 1/2. And if the coin is flipped twice, the probability of getting two tails in this situation, one winner out of 4 possibilities. Now, to flip a coin 3 times, we're going to extend that one more level. First flip is either heads or tails. Knowing the first flip is a heads, second flip is either a heads or tails. Knowing the first flip is a tails, second flip is either a heads or tails. So this would be the sample space for flipping 2 coins. Now, to flip 3 coins, you've got to start with HH. 2 possibilities for the third, either H or T. Then we go to HT. 2 possibilities for the third, either H or T. Then we go to TH. 2 possibilities for the third, either H or T. Then we go to TT. 2 possibilities for the third, either H or T. So our sample space, HHH, HHT, HTH, HTT, THH, THT, TTH, TTT. And once we have the sample space, we can answer questions about various probabilities. So we've tossed a coin 3 times, probability of 0 heads. That would be this case, 0 heads, TTT. We get 0 heads 1 out of 8 times. Exactly 1 heads. Where do we have exactly 1 heads? There's exactly 1 heads. There's exactly 1 heads. And there's exactly 1 heads. So we have 3 winners out of 8 possibilities. Exactly 2 heads. Here's exactly 2 heads. Here's exactly 2 heads. Here's exactly 2 heads. Again, 3 winners out of 8. And exactly 3 heads. That's our first case, 1 out of 8. So you'll notice you have a 1-3-1 situation happening there. If we toss a coin 4 times, that pattern continues. And you probably wouldn't want to express a sample space for tossing a coin 5 times. With 4 times, there are 16 numbers in our sample space. If we want 0 heads, here's our only case for 0 heads, TTTT, 1 out of 16. How about exactly 1 heads? Here's 1. Here's 1. Here's 1. And here's 1. So you can see the answers. 0 heads as we saw, 1 winner out of 16. 1 heads as we saw, exactly 4 winners out of 16. 2 heads is going to give us 6 winners out of 16. 3 heads, 4 out of 16. 4 heads, 1 out of 16. Well, we can certainly use the computer to help us identify these sorts of probabilities. So we're going to use MINITAB to simulate flipping 4 coins. So the commands here, random 100,000, pretty good number, C1 through C4. And then we're going to say Bernoulli 0.5 period. Always end your subcommands with a period. And what does Bernoulli do? Bernoulli either puts zeros or ones in the columns. 50% of the time we get zeros, 50% of the times we get ones. So we're going to perceive the ones as heads, and we're going to perceive the zeros as tails. So looking at some output, you can see we had a tail, a tail, a tail, and a head. So for our first row, we would have gotten 1 heads. Second row, 1 heads. Third row, 1 heads. Fourth row, heads, 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 heads. The fourth row, each is heads. That would correspond to flipping 4 coins and getting 4 heads. So the command that we use is let. We're going to say let C5 equals C1 plus C2 plus C3 plus C4. That will add all of the heads together. And there you can see 1 heads, 1 heads, 1 heads, 4 heads, 3 heads, 1 heads, 3 heads, etc. But I have done this several thousand times, I believe 100,000 times. So we're going to need to figure out exactly how often we had 1s, how often we had 2s, 3s, 4s, etc. So the command that we use for that is table C5. Table C5 will go ahead and tabulate all those results. And there you go. You can see 0 heads showed up 6,178 times. 1 head showed up 24,957 times, etc. And then we can look at our various probabilities. So these are approximate probabilities based on simulations. So the question is, are those approximate probabilities close to the theoretical probabilities? So here's our simulated probabilities, and here are our theoretical probabilities. So our simulated probability 0.06178, our theoretical probability 0.0625. So you can see good to 2 or 3 decimal places, pretty good. 24957 compared to 0.25, pretty good. 37423 compared to 375. 25100 compared to 0.25. 0.06342 compared to 0.0625. Now the law of large numbers tells us that as the number of trials goes to infinity, the simulated probabilities should get closer and closer to the theoretical probabilities. So if I wanted better answers, closer answers, rather than using 100,000 trials, I might use 1,000,000 trials or 10 million trials. We can also use Pascal's triangle to help with some of these problems. Take a look at how we identify the numbers in Pascal's triangle. We start with a 1, and 1's on either side. Then we add the numbers together. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5, etc. And that trend continues throughout the triangle. So we're going to ask a question. If you flip a coin 6 times, what is your probability of getting 0 heads, 1 heads, 2 heads, 3 heads, 4 heads, 5 heads, 6 heads? You've got to go down to the row that has a 6 in it. So it's this row right here. If you add up all those numbers, you get 64. 64 is going to be the denominator for the fraction. So getting 1 head should be 1 out of 64. 2 heads should be 6 out of 64, etc. So you will see those probabilities. 3 heads, 15 out of 64. 2 heads, 15. 3 heads, 20 out of 64. 4 heads, etc. And of course, you could also do this with 7. If we're flipping a coin 7 times, we are now looking at this row, the row that has 7 in it. This will correspond to 0 heads, 1 heads, 2 heads, 3 heads, 4 heads, 5 heads, 6 heads, 7 heads. So if we look at our probabilities, what do we get? There are all the probabilities, with 128 being the total number of elements in that row. 128 is the denominator, and the numerator is 1, 7, 21, 35, 35, 21, 7, and 1, taken directly from Pascal's triangle.